Hi, welcome back. And we're in boundary layers today. Okay, so this is good, good amount of fun. And boundary layer. And we did a little bit of turbulence, but this is actually there's some pretty interesting things within boundary layers that we'll hear talk about, and then we'll actually talk about some kind of higher level flows, things like that. So boundary layers. So generically, you got, usually this way you got a surface and then your boundary layer is growing, right? And as a definition, normally this boundary layer, we're talking about how the flow eventually gets up to this U infinity, and you might have a couple ways of defining it. So sometimes it's defined as the layer is at 99% of U infinity, things like that. So you gotta watch in your definition, there's lots of people that argue on it. Eventually, this boundary layer can incur transition to turbulence. This might be a laminar boundary layer, things like that. But one of the ways we characterize this is through displacement thickness and momentum thickness. And so what you would do is say, well, actually, this is a velocity deficit. That line would represent U infinity. And so this, call it an area, is the deficit. And I could equivalently talk about how if it didn't have a shape, my boundary layer didn't have a shape, if it literally went from U infinity all the way down to 0 at some height del star. Okay, so this is called this displacement thickness. Displacement thickness. Okay, and its definition is then just an integral. So again, you would say del star is an integral from 0 to y of rho u dy, and that's going to be equal to integral from del star up to y of rho ue, e being sort of the edge of the boundary layer. In case there's any difference in density as well as velocity, it may not necessarily be free stream. So that's sort of the definition. Okay, you can actually recast this and solve for it. So usually the way you see it, so this is how you would naturally form it. It's what I did graphically. You go back and solve it, it's going to be integral from 0 to y of 1 minus rho u over rho the edge of the boundary layer dy. That's displacement thickness. It's effectively a conservation of mass point of view. And so you can actually replace, do the same sort of thing as, and call it momentum thickness. Okay. And momentum thickness is, we usually use a theta to describe that. And that would be an integral, again, from 0 to infinity, u over u infinity 1 minus u over u infinity dy. It's actually built the same way up here, where you just say it's a deficit of momentum. And so it's a rho u squared, and then you can solve for that. And this is what you end up getting. Okay? And so momentum thickness is nice. In fact, sometimes, while usually a boundary layer, you might talk about the Reynolds number based on x, like the distance x from the tip of the boundary layer. A lot of times people will say, no, that's not the right way to characterize it. I'm actually going to be I'm not looking for Rex. The better way might be Re theta, because this is the distance. And so this would be rho times velocity u infinity times theta over viscosity. And so you'll see that a lot. Okay, this is usually a little bit way to do it. And one of the reasons for that is you can actually go to the momentum equation, and you can come back and you can show this relation that the change, the gradient of, again, the free stream top velocity may be changing. Think about an airfoil where U infinity is coming at the aircraft, and then the top of the boundary layer is actually going to accelerate over top of the airfoil or slow down. So u edge squared times theta plus u edge, and then the change of the velocity outside the boundary layer with respect to x times the displacement thickness is actually equal to the wall shear stress. And so this is one of the ways you can actually go back and sort of define some things and calculate shear stresses and things like that. It's actually related to this. Or in other words, if you know your shear stress, you should be able to figure out your kind of your momentum thicknesses. Okay, and so we can actually come and use this in a couple of different ways. So one is, go back to that Joukowsky airfoil we were talking about last time. So if I have an airfoil that looks like this, and remember this maps over to a spinning cylinder that's sort of off axis, right? Which means we can get the full velocity field over this thing. And so when we do that, we can actually take a look at, this is all kind of normalized. So U, this would be U over U infinity. So it goes greater than 1, remember, because the flow speeds up around the airfoil. And then this line is like 10 times the displacement thickness over the length. And then another line here, I'm going to switch colors so you can see it. By the way, this is, in Panton, this is Fig 20.4, for a very kind of famous diagram of this. But that does this. This is actually beta, and beta is a pressure gradient. Okay, we'll talk a little bit more where beta comes from in just a second. Okay, but this is you kind of use this information and to calculate ultimately displacement thicknesses and different characteristics of kind of the boundary layer going around, something not just a flat plate. So our flat plates are interesting because it's very calm. You can look at different stuff. Actually, most of the real world occurs in things like airfoils or boat hulls or that kind of stuff. And so it's all kind of part of it. Also in this chapter, even though the chapter is labeled boundary layers, really, it's almost kind of back to some similarity in higher Reynolds number flows. Panton does talk through, I mentioned this a little bit last episode, that this is a free jet and how that jet is going to sort of spread. So it might start as a square wave jet, but then it's going to spread and the height is going to come down. So there's a similarity there that should be very kind of familiar to when kind of last episode we were talking about, last chapter was talking about the flow over a wake. Okay. But then one of more favorite ones that I like as well is actually shear flows. And so if here's an interface and you say you have high flow over low flow, just a shear, right? Then you actually can get some, the mixing and turbulence is kind of going to grow. Now on top of that, if you actually have a density difference, this is in kind of Kelvin-Helmholtz, and some pretty beautiful stuff you can see. So there's some really, if you've ever seen these beautiful pictures of like clouds and things like that, this is what happens when you have a shear layer, and this is a shear layer instability, kind of growing into these very regular curls. And if you zoom in, you'll see curls again. This is some of the more picturesque fluid instability, then transition to turbulence that you'll see. Okay, but again, the shear layer is going to kind of grow. There's some models based on how it grows and things like that. It's all kind of back to this. Okay, and then I'm going to finish here with a couple different things, but one, back to this beta. And so we did a little bit of kind of non-dimensionalization and talking through some of the power of that and similarity variables. And so there's one called Falkner-Skan. And to just write down the equation here, what you end up doing, so this is where again f prime is equal to u over u edge, and then just as definitions, let's see, eta, which is a variable that's primed on eta, is equal to y, and then square root of the edge velocity over nu times x. That's your similarity variable. And so when you do kind of the momentum equations and conservation of mass, you end up getting this equation that's f triple prime. And we've seen this before a little bit with stuff, plus 1/2, and then there's a beta that gets kept in there, plus I, f double prime, oops, just double prime, plus beta, and then 1 minus f. And then that is squared, right, equals 0. Okay, so this equation you can solve. It's actually just a first order equation. Usually it's solved numerically. But what's neat about this equation is beta equals 0 is flat plate, and beta equals 1 is stagnation flow. And then between beta and 1 is actually like a wedge. So you can actually solve, again, some of these things. There's kind of the Joukowsky method, but there's also the Falkner-Skan method. And that's what this beta is. So beta here would be at 0 because it's actually pretty quickly becomes 1 because it's basically a stagnation. And then goes greater than 1. And so it's has a pressure gradient, and then less than 1. And yeah, so it's pretty interesting, and eventually kind of cycles back to a flat plate. So again, back to the power of what you can do through analysis and really learn a lot about what's happening to the edge, what's happening to the pressure gradients, can we track what's happening to the displacement thicknesses, things like that. Okay, I'm going to finish with a couple interesting ones. And the last one that's in this chapter, again, is really kind of interesting. That's why I like kind of the graduate level work is as you're reading through it, you're actually getting these pictures of real flows and real interesting like transitions. Right? It's not just Bernoulli equation. It's not just quick basic turbulent flows. Some of them can be really, really beautiful. So take a look at this one. Okay, this is called Taylor-Couette. I'll write it here. And this is basically flow between two cylinders. I'll write it like this. Okay, so what you're doing is you're sort of rotating this inner cylinder, and this is very, very thin compared to it. Now, under some speed, you're just sort of dragging all the fluid with you. But when it starts getting above some speed, it's actually unstable, and you pop to, if we're looking sort of end-on into this cylinder roll, you actually pop into some convection rolls. Okay? And so yes, the main flow is still going around, but you develop this sort of secondary motion that just goes unstable. So just beautiful. And then as you turn up your speed, you'll start getting waves and things like that. So watch this YouTube video. Okay, and so the experiment is starting. I'll try and get out of the way here. And now we're starting to see the first kind of just rolls showing up. There we go. And then as you're turning faster, you start seeing the waves. Right? And then it gets a little more unsteady, more wavelengths start popping in. And then eventually it's going to just kind of break down and go into turbulence. So there's a whole range of flows that are just interesting, and transitions and dynamics. So it's a real rich area of study, especially in academia, in terms of applications in the real world. These things happen all over the real world, and so it's a good. Again, that's why I like teaching this course sort of as this combined. So you're not just walking out of undergrad fluids with like Bernoulli equation and things like that. It's a little bit more math, but to understand that there are some flows and there's some instabilities. Too many times people just are like, it's turbulent, it's just increase in drag. It's like, no, there can be all sorts of things, and especially that kind of transition to turbulence in different fluid regimes. So we'll see you next time. And remember, I'm going to read these chapters, kind of 20 and 21, and we'll see you next time.